All right. So it's a little bit of a mouthful of a title, but what I want to talk to you guys today about is a relatively new technique in terms of how we combine geochronological data and geochemical data from in situ laser analyses of datable accessory phases. So I wanted to start out just by acknowledging the contributors and collaborators in this study. The first three are students of mine, Victor Guevara, who just finished his master's and is now a PhD student at Virginia Tech, and then my current graduate students, Leanne Stevens and Drew Kramer, and then colleagues at UM and UC Santa Barbara in Florida. Okay, so today I wasn't sure what the background would be with everybody, so I'm going to start out with a little bit of a primer on radiometric dating in geology, and so I apologize if that's a little bit of a review for some of you, but I wanted to give you a little background on uranium, thorium, lead dating, and then I'll talk about the technique of laser ablation split stream, or LASS geochronology. And I have data to show you from three different areas. The first two are from metamorphic core complexes in the northern Idaho panhandle, and the last example, which we'll hopefully have time to get to, is from the Ruby Range, a little bit closer to home here. Okay, so you know, why is geochronology important? Well, I would argue that the knowledge of rock formation ages is probably the single most important tool for assembling the geologic record into a coherent history. So we can go out and do spectacular field work, but to really put things into an absolute time framework, we need to obtain good age data within that geologic context. And in terms of all of the isotope systems that are available to geologists to use, for rocks that are on the scale of millions to billions of years old, it's the uranium, thorium, lead decay system that's played the most central role in quantifying geologic time. And that's because the half-lives of these radioactive isotopes, uranium and thorium, are long enough on the scale of hundreds of millions to billions of years, such that they're relatively easy to measure in most rocks that range from millions to a billion years or more. So just a little bit of a primer on geochronology. What we're interested in here is measuring the ratio of parent radioactive isotope to stable daughter product. And if we can measure this ratio in a mineral grain that contains a radioactive isotope, then we can calculate an age. So the idea here is we have a mineral grain acting as a little hourglass, where the parent isotope is going to decay to a stable daughter product at some known rate, and that rate is called the decay constant. And that decay constant changes for any given parent isotope. And so if we know that rate at which it decays, we measure through mass spectrometry the parent-daughter ratio, then we can calculate the time at which that crystal formed. And when we talk about radioactive isotopes, we talk about them in terms of half-lives. In other words, how long does it take if we start out with 100% parent? What's the time at which 50% of that parent isotope has changed or decayed into the stable daughter product? So in that case, the daughter equals parent. That ratio is 1. So the expression for time reduces to this equation. So we can calculate what the half-life for any given isotope is. And the decay constants are something that we know relatively well. There's a little bit of debate on, there's an error on that measurement, but we know for the uranium, thorium, lead system, we know those decay constants quite well. And in the geologic dating that I'll talk about today, the three isotopes that we're interested in, the three parent isotopes, are uranium-238, uranium-235, and thorium-232. And they each decay to different isotopes of lead, 206, 207, 208, with varying half-lives, ranging from several hundred million years in the case of uranium-235 to 14 billion years for the thorium isotope. And just to remind you, in terms of what we're talking about when we talk about isotopes, this number here is the atomic mass of that particular element. And what's different with isotopes, for isotopes of the same element, like uranium-238 and 235, is there's a different number of neutrons in that atomic nucleus. So this is just an example for hydrogen. A typical hydrogen has 1 proton, 1 electron. If we add a neutron to that, we get a heavier isotope, hydrogen-2. If we add another neutron, a even heavier isotope of hydrogen-3. So that's what we're interested in, is these particular isotopes that happen to be radioactive or unstable that are going to decay to a stable daughter over geologic time. And so the typical way, and my training as a geologist was in conventional, what we call conventional geochronology, which essentially involves going out and collecting a whole lot of rock, coming back to the lab and crushing that rock up, and then putting the material, the sand material that you generate, through a series of separation processes, including putting it over a, essentially a gold panning table, separating minerals out based on their magnetic susceptibilities, and then ultimately using a high-density heavy liquid to separate out the minerals that we're interested in. And these minerals that are datable are typically heavy, high-density minerals because they contain uranium and lead, which are heavy elements. So in a heavy liquid, they sink. We can extract them. With a little more work, we can get a purified split of these minerals. And then we can pick them under the microscope, and we can, in the laboratory, dissolve them in acid and go through a series of chemical separation steps to extract uranium, thorium, and lead. And then in conventional mass spectrometry, once you have that separation of material, you put it on a little filament that has a thin rhenium wire stretched across it. Looks a bit like a light bulb filament, and your sample goes on top of that little piece of rhenium. You put that in your mass spectrometer here, you heat it up, apply a high voltage current, and ionize those uranium and lead isotopes and measure them in a mass spectrometer. And so that works really well, and up through the 1960s, 70s, 80s, 90s, and even today for high precision ages, that's the typical method that we utilize, is to extract the minerals from the rock and get a high precision age on a single grain of material. Okay, so another thing we have to worry about when we do geochronology is, what if this hourglass, this system where we have the decay of parent isotope to daughter isotope, what if there's a leak in it? And the way that that can happen is if we heat up the rock enough at some point, either as it's forming or later in its history, such that the daughter isotope diffuses out of the crystal. And in that case, we effectively lose that daughter isotope. And when we go to measure the parent-daughter isotope ratio, we don't get a geologically meaningful age. Or in the case of certain minerals, what we actually obtain is a time at which that mineral cooled through a particular temperature that reflects when that mineral closed to that diffusion. For the minerals that I'm going to talk about today, which are monazite and xenotime, that isn't really an issue because the closure temperature for monazite is over 900 degrees. So if you don't have an event that's heating the rock up to above 900 degrees, then that age that you get is likely to be pretty robust. Same thing for zircon, the other commonly dated mineral. It's greater than 900. For xenotime, which is very similar to monazite, it's just a heavy rare earth element phosphate instead of a light rare earth element phosphate. It's never, the closure temperature hasn't been measured experimentally on that, but it's likely to be in the same ballpark as monazite because it's a similar crystal structure in chemistry. So for these two minerals, monazite and xenotime, they're really abundant in metamorphic rocks, particularly in metasedimentary rocks, and they are very radiogenic, more radiogenic than zircon typically, particularly with respect to thorium content. So they're very amenable for geologic dating. Okay, the diagrams, you're going to see a lot of these throughout the talk, and this kind of diagram is called a Concordia diagram. And this particular type of diagram is called a Tara-Wasserberg Concordia. And the idea here, what we're plotting is, we're plotting the 207 lead to a 6 lead ratio versus the 238 to a 6 uranium 206 lead ratio. And this line here, the black line with ages on it, is called the Concordia curve. And so if a mineral grain has remained closed, has never lost any daughter isotope, it's going to plot on that curve, like this blue dot. But if there's been some disturbance to the system, in other words, if it's been heated up and it's lost daughter isotope, then what we'll see is that instead of being concordant, it'll plot like one of these red dots and reflect some kind of isotopic disturbance. Alternatively, you could have, in a metamorphic terrain, you could have two metamorphic events that have occurred. Or you could have an igneous crystallization event and then a metamorphic event that overprints that. So you might have two or even more than two age populations. But if you just have two, it's relatively easy to decipher on a diagram like this because your younger event will plot at some point here, your older event here. And if you're getting mixed stages, mixing of those two components, then it'll look exactly the same as if there was isotopic disturbance. So it's a very useful kind of diagram for deciphering more complex histories and to see if the different isotopic systems reflect mixtures or have been closed systems since the formation of that mineral. The other thing I'll point out on the Terra Wasserberg is that we could detect recent lead loss, which would pull it in a horizontal direction. In other words, just present day diffusion of the daughter out. And the other thing that you can detect is if the grain has non-radiogenic lead in it, which we call common lead, basically just dirty lead, that's in that mineral structure, what that'll do is pull it straight up. And so you'll see points that plot above this Concordia curve, and they're still good ages, but they just reflect that there's some non-radiogenic lead that's in that mineral grain. But we measure that and can account for that. Okay, so with what we call conventional geochronology, the main tool that's used is something called a thermal ionization mass spectrometer. That's what I just described with the little rhenium filament where you heat it up and the uranium and lead atoms ionize. That's the most precise technique. That's where we can get the most precise, lowest errors, best age from. But it requires that we actually dissolve the mineral grain. We put it into a solution, the entire grain typically, and get an age. So for a complicated grain that might have an inherited core and a younger metamorphic rim, we could detect that as a mixed stage. But alternatively, what we could do is use some type of in situ method where we actually drill a small hole in the crystal and measure the core and the rim with that spatial resolution. And the two techniques that we can use for doing that are utilizing an ICP-MS, which is a plasma source mass spectrometer with a laser on the front end. So we use a laser to ablate a small hole or pit in the grain and measure that material with high spatial resolution. The other technique is to use a similar, ion microprobe, but that uses a stream of ions that ablate the sample effectively. Both have a similar precision, and so this pink bar shows, if we measured 9 grains by ID10s, we could get our error on a 100 million year old grain down to probably within 0.03%. So really high precision. If we do the same thing, 100 million year old grain with either the shrimp SIMS laser ICP-MS, we're going to, at best, with measuring maybe 25 grains, get within 1%. So it's much lower precision, but you have the advantage of having really high spatial resolution. So for complex grains, like this one here, if we had, let's say, for example, we had a 1.8 billion year old core of a mineral that then grew a younger rim, we can actually put a laser down and measure those two zones within a single crystal and get a pretty precise age on the time scales of each of those events. You could do a similar sort of thing with if you had zoned a progressive growth over a period of time in a crystal, as long as that progressive growth is on a time scale that's resolvable within the error of your analytical technique. So using the in situ methods are fantastic for complicated rocks, and most metamorphic rocks tend to be complicated rocks. Okay, so the minerals that I'm going to talk about today are rare earth element bearing phosphates, monazite and xenotime. Monazite is a light rare earth element phosphate. Xenotime is yttrium phosphate, but is very compatible with the heavy rare earth elements. And monazite, it's a widespread accessory phase that we see in moderate to high grade metamorphic rocks, particularly metasedimentary rocks, metamorphosed shales and mudstones and so forth. Xenotime is less common than monazite and tends to be more often observed in lower grade rocks, upper green schist to lower amphibolite facies. And what typically happens with xenotime is that as progressive metamorphism occurs, because it's a heavy rare earth element phosphate, what it tends to do is break down, release those heavy elements, and then the yttrium immediately goes into the garnet. And once the yttrium starts going into the garnet, the xenotime tends to break down to form new monazite, and the yttrium goes into the garnet. So we don't usually see it at the same amphibolite facies conditions as monazite, unless it happens to be a very heavy rare earth element rich or yttrium rich environment. But it does tend to come back later in the rock's history if we get to conditions where the rock starts to melt. It's very common to see xenotime in melts, because what happens then is that garnet tends to be broken down, resorbed during melting. It releases heavy rare earths and yttrium, and it's common to see it in leucosomes and leucogranites and that sort of thing, anything that involves crustal melting processes. So both minerals are really important for measuring what I would call typical regional scale metamorphic processes that occur at amphibolite facies. So with the petrochronology, with the laser ablation split stream technique, what we're doing that's different is that in addition to measuring grains in situ, we're actually coupling together two mass spectrometers, two plasma source mass spectrometers, and a front end with a laser. And what we do is we ablate the sample with a laser, and then we have the Teflon tubing that splits off into a T, and 50% of our laser, the stream goes into the mass spectrometer to measure age, or the uranium, thorium, lead isotopes, and the other 50% goes to a second mass spectrometer to measure, in our case, we're going to look at the rare earth elements. But you have lots of options for how you combine your two mass spectrometers together. When we measure zircon, we typically couple it with hafnium isotopes. With monazite, we can actually also couple it with neodymium isotopes. So it depends on what kind of geologic question you're answering. If you have questions related to sources of magmas and that sort of thing in igneous environments, you probably want to couple it with neodymium or hafnium. With zircon, with metamorphic environments, we find that the trace element, the rare earth element signature, is critical for deciphering when that monazite grew relative to what garnet is doing in the rock. So the key is we're basically making two measurements on the same aliquot of material. And so this is just one example here where this is a rock that has a highly resorbed garnet. All the blue dots here represent xenotime grains that grow in this resorption zone around this garnet. So petrographically, we observe that these are related to garnet breakdown. And this is a backscattered image from the SEM of one of these xenotime grains. And when we date these, the blue circles here all correspond to the xenotime analyses, the red are monazite in the same rock. They all yield 48 million-year-old age. So in this case, we can actually, and we're doing this work in a thin section. So we're not separating the minerals at all. We're just doing it in a standard polished 30-micron thin section. And so we can analyze that grain in its petrographic context and get an age on it. And in addition, we also measure the rare earth elements. In this case, it's all forming at the same time, so it has a completely uniform rare earth element signature. Okay. So just to run through kind of the method from start to finish of what we do with the samples, and then I'll start showing you some data. The first step is to find the monazite and xenotime grains in the thin section. So we take a standard petrographic thin section and go to either the SEM or the electron microprobe, and we obtain X-ray maps, chemical X-ray maps of the different elements in that thin section. And so this just shows the overall kind of rock mineralogy with an aluminum map. And then what we also collect for monazite, to identify monazite, is we collect a cerium map, and for xenotime, a yttrium map, and for zircon, a zirconium map. And then they're really small, usually 100 microns or less in size. So then we just go in and Illustrator or your favorite graphics program and highlight little circles where we see little white specks on that map, which correspond to where those grains reside. And then we will select which grains we want to go after with the ICP, usually the biggest ones, and also ones that are in important petrographic settings. So we almost always want to look at inclusions and things like garnet and kyanite, because they might help us decipher the metamorphic history. So we select anywhere from 8 to 10 or more grains that we want to date. And this is just that same location map then overlaying on just a scan of the thin section, so we can see kind of petrographically where these different grains are in the rock. And then what we do is, again, either using the SEM with the EDS or with the electron microprobe, we obtain element maps of the grains themselves. So this is one single monazite grain, and we collect, in this case, yttrium, uranium, calcium, thorium, neodymium. And it's usually the yttrium or thorium maps that are interesting in terms of if there's zonation present. And so we do this to guide the choice of where we want to actually put the laser spot down. So if in this case, we would definitely want to try to measure this high yttrium zone and then get measurements in the low yttrium zone. And so this shows that where we actually put the spots down, and you can get a sense of what the size is of the spot. So these are 10 micron spots on this screen. So we use that X-ray map to guide our analysis, trying to capture different zones of where the chemistry changes or where the age might change. And then all of this work that I'm going to talk about today was done at UC Santa Barbara. There's only a few labs in the country that are doing this now. And the main reason for that is that it requires that your lab actually has 2 mass spectrometers. There's even fewer places that are doing this with monazite. So Santa Barbara is really, right now, one of only 2 or 3 places that's doing this with monazite. There's more labs that are routinely doing this kind of work with zircon, including Washington State University is one that's got it set up for zircon. But the idea is that we have a front-end excimer laser. Our sample is just a standard thin section. The laser beam hits the sample, and then the material is ablated and split into 2 streams. One stream goes to a single collector ICP that measures the rare earth elements, and the other aliquot goes to a multi-collector ICP that measures all the uranium, thorium, and lead isotopes. So within 1 minute, the whole analysis takes a minute for each spot. We can get simultaneous age and geochemical information. So what it looks like in an analytical session is basically you just have to have those thin sections prepped. For monazite, we do a 10 micron spot size because it's so radiogenic, high in thorium and lead. We can get away with that for monazite. For zircon, it's usually more of a 25 or 30 micron spot because it has lower concentrations of those isotopes. Typically, we'll do anywhere from about 30 to 80 analyses in a thin section. Just depends on how complex it is, how many grains we have, how big they are, how many spots we can put down. But in a session, you can, basically each analysis takes a minute. So you can get through roughly about 50 per hour. Then you'll have to also have a time to set up all of your, relocate all your grains and set up all your spots. And that actually takes longer than the actual analysis. So each thin section is probably about a 3-hour job from start to finish. So you can crank through a lot of samples in a session. And the error that you end up with generally we've been getting about a 1% error on our 7-6 ages. So it's a pretty efficient technique. And that's in comparison to dissolving the grain via ID-TEMS, which takes, typically we don't do more than about, 5 or 6 grains from a sample, and each analysis takes hours. So in a day you can crank through, a half dozen as opposed to in a day here capturing literally a couple hundred ages usually. Okay, so I want to show you a few different data sets using this, and the first is from, I've been working the last few years on the metamorphic core complexes in the northern Idaho panhandle. And what metamorphic core complexes are domal uplifts of mid-crustal metamorphic rocks. In the northern Rockies area, they're typically exhumed from 25 to 35 kilometers depth. And these are here, they're exhumed because of the post-orogenic extensional processes that occur. And so basically you have convergent tectonics occurring, building up a mountain range, thickening the crust, and at some point that crust becomes gravitationally unstable. You build up topography to the point that it becomes unstable, just like a pile of sand at the angle of repose. and it collapses under its own weight effectively. And it generally will begin collapsing at the point that you slow down convergence rate substantially or stop convergence. And then it induces this instability and you start extending. And in the case of the Northern Rockies complexes, which are shown here in blue, these were all exhumed during the Eocene, the Anaconda, Bitterroot, Clearwater, Priest River, at around 53 to 50 million years ago. In the complexes, we've mainly been working in the Priest River and Clearwater, a little bit in the Bitterroot, but they're all developed within strata of the belt supergroup. And it makes for a nice comparison between the metamorphic histories because we have similar protoliths between the rocks and the different footwalls of these complexes. So if we look at the Priest River first, the highest grade rocks in the core of this complex are metamorphosed rocks of the Pritchard Formation and the belt supergroup. They've been metamorphosed to upper amphibolite facies. They're migmatitic, but relatively low melt fractions. So they're not soupy migmatites, they're just kind of barely migmatites. And the extension began around 53 million years based on dating of these syn-extensional plutons, Eocene plutons in the region, the Rinko and Silver Point. And so my PhD student, Leanne Stevens, has been working on this project. We looked, using the laser ablation split stream, we looked at samples of the Hauser Lake Gneiss, which is this metamorphosed Pritchard rock. And it's a high-grade garnet, sillimanite, K-feldspar rock. And in the core of the complex here, right around the town of Spirit Lake, the stable aluminosilicate is kyanite. Everywhere else it's sillimanite, but in these three samples here in the core, these are the most deeply exhumed rocks, and kyanite is stable. So it's relatively high pressure. Leanne's done the pressure temperature history of these, and the peak metamorphic conditions based on the metamorphic assemblages are around 10 kilobars, which is about 33 to 35 kilometers depth, and around 750 to 800 degrees. So they're pretty high-grade rocks. And then we do this metamorphic phase equilibrium modeling to look at the pressure temperature history. In other words, where in the crust was it when it was metamorphosed. We can also look at we can model how much melt that rock would have had. In this case, we estimate the amount of melting it's undergone is around 20% or something just under 20%. The garnet, these are garnet X-ray maps. The garnet in these samples is completely unzoned, which is another indication that it's seen very high temperatures. In garnet that's formed during a progressive cycle of metamorphism usually reflects some kind of zoning, but if the temperatures get hot enough, these profiles just get flattened out and re-equilibrated by diffusion. So this rock has seen quite high temperatures, it's melted, and so a high-grade rock. And when we look at the laser ablation data for this, this is for one sample, we see two different populations of ages in this sample. The oldest population is Cretaceous, ranging from about 65 to 75 million years. And that petrographically is linked to inclusions in garnet and kyanite in the sample. So when we date an inclusion inside one of these porphyroblasts, we get Cretaceous ages. In contrast, there's a second population that occurs in the leucosome, the melt in the rock. This is an inclusion in a ribbon of melt, basically. And that yields younger ages, between 55 and 50 million years. So we see these two age populations in the same thin section that we can now correlate to the growth environment of that particular mineral grain. And when we look at that in terms of the geochemistry now, this is just a Concordia diagram that plots the thorium-lead age versus, or thorium-lead ratio versus the 206 lead 238 uranium ratio. And these are color-coded from oldest to youngest. So the oldest are coded red, the youngest are color-coded blue, and the same colors are used on this rare earth diagram. So we're looking at the rare earth chemistry change as a function of age. And what you see here is that from this growth of red to turquoise, there's a decrease in the heavy rare earth elements as you go from the oldest to the youngest. And that reflects the change that as garnet is crystallizing, it's actually the heavy rare earths are going into the garnet and depleting it from the monazite that's growing later. So this is a very common pattern to see during prograde metamorphism. As you're growing garnet, you lower that reservoir, and the monazite reflects that. But what happens with the younger population is that then these blue analyses, they're now higher in the heavy rare earths and form in the melt. And what that's telling us is that the garnet was resorbed and reacting during that melting process that occurred much later. So that's a nice example of how we can use that chemistry to have more confidence in the interpretation that this is our cycle of prograde metamorphism, and this is related to decompression and crystallization of melt as these rocks are being exhumed. Okay. And in the Priest River area, we've looked at 5 different samples across the complex, and we see similar. This is just an aggregate of all of the data. And the ages that we see range. The oldest that we measured was 94. And we had a few ages that were up in the 80s and 90s. And those ages are from a sample, if I just go quickly back here, right at the edge, literally less than a kilometer away from the edge of the Kaniksu batholith, which forms the Selkirk crest. And that batholith is about 90 to 100 million years old. So our interpretation that we think is going on there is that that particular rock was affected by contact metamorphism from the batholith intruding and grew some monazite earlier in the Cretaceous, but it's still, the same sample still records the 65 to 75 event in it as well. But other than that, all of the other 4 samples record very consistent age range that reflects this prograde cycle of metamorphism in the Cretaceous, and then the younger growth, which is restricted to the leucosome material in the rocks. Okay, so that's the Priest River, and the Priest River is this massive core complex that forms a bunch of the northern Idaho Panhandle. The Clearwater core complex, in contrast, is a teeny little core complex that's just south of the Clearwater, or just south of the Priest River, and it also occurs right within the Lewis and Clark line, which of course is a big dextral strike-slip fault system. So the northern and southern boundaries of the Clearwater complex are actually bounded by these big strike-slip structures of the Lewis and Clark. So it's not structurally, it's not as simple as just having some big normal fault and exhuming the rocks. It actually involves some of this strike-slip faulting to bring the rocks up. So structurally, it's a lot more complex. It's also developed within strata of the belt supergroup, but the core of the complex, which in this yellow area here, which corresponds to this region here, is basement rock. So it's Paleoproterozoic basement that's about 1.8 billion years old that forms the core. It's what was below the belt. So we actually see the bottom of the belt, the Neihardt quartzite on top of that, and then the belt strata. So it's a pretty neat place for seeing that, basically the bottom of the belt basin exposed. But the cooling ages, the mica, argon cooling ages in this area are all Eocene in age. So within this sort of gray zone here, which is the Clearwater complex, the cooling ages are younger. When we move west into the strata, the Wallace Formation strata, we actually obtained a Proterozoic mica cooling age of 1380 million years. So over here we had a Proterozoic argon cooling age, and on the eastern side it records Cretaceous cooling. That's in the range of 60 to 65 million years old. But within this sort of gray zone, we see younger ages, indicating this whole thing has come up from depth during the Eocene. And that's just the cross-section line for this diagram here. So just to simplify that map just a little bit to outline just the complex. So these are the basement rocks in the core, and then the gray are essentially mapped as we don't know what age they are, but they're high-grade metamorphic rocks. And so I've been doing a lot of work on these rocks to try to figure out the metamorphic history, because it could be related to Proterozoic history, it could be related to the Cretaceous history. And so I just want to show you data from a few samples. We've actually dated a lot of samples from this area, but just to highlight the different types of data we're seeing, I'll show you a few. Also to note, these purple ages here are garnet ages that Jeff Vervoort at Washington State University has obtained. And so in a study that he did of this region, he found that all the garnet lutetium hafnium ages were Proterozoic, ranging from 1.3 all the way down to these Grenville 1.1 ages. And the most interesting rock in this area is right within the internal zone. So I'll show you some data from the internal zone here, the yellow, and then we'll move to a rock that's right in the shear zone, and then I'll show you one from the west side, and then one outside the complex to the east. But this rock is the basement schist unit in the internal zone is called the Boehls Butte schist, and it's associated with a Paleoproterozoic anorthosite. And the interpretation in terms of the petrogenesis of this rock is that the anorthosite intruded 1.78 billion years ago, and when it intruded, the aureole surrounding it, the rocks surrounding it were metamorphosed in a contact aureole, and these are sediments. And in that process, what happened was, and they underwent partial melting, and aluminum was enriched in that new metamorphic rock, and other elements were lost. Mainly silica was lost by fluids and melt carrying it away. So you ended up with a protolith that was really enriched in aluminum and also in iron and magnesium. And so what you end up with is this very feldspathic biotite-rich schist that contains upwards of 30% aluminosilicates. These knobs on this outcrop are all large kyanites in the rock, so centimeter up to foot long, centimeter to foot long kyanites, and they've now been almost entirely transformed to Andalusite. So you can see the pinkish color hopefully here. So original kyanites that are now converted to Andalusite. And garnet is scarce in this rock, but when it does occur, it tends to be very large, centimeter to several centimeter diameter garnet. And Jeff Vervoort at WSU obtained a garnet lutetium hafnium age of 1463 million years on this particular locality here. And that was from a core. What we see when we look at these garnets in detail, though, is that they're really complicated. They have an old core that is Proterozoic, but then they have this high calcium, low manganese rim surrounding that perfectly euhedral core. And this increase in calcium and decrease in manganese reflects an increase in pressure from the core formation to the rim, that change in chemistry. So low pressure core, high pressure rim, and the inference is that we have an age date on that of 1463. The rim, Jeff's tried to get some data on rims. It becomes difficult because what happens is all your lutetium goes into growing the core. You have these very low lutetium rims, and you can't get very precise ages, but he's gotten some Cretaceous, with big errors on them, ages on the rims. So presumably this is related to the first metamorphism, that's essentially the age of the belt deposition, and then a second event that's the Cretaceous high pressure event. And we do a similar sort of PT study on these, and I won't go into a lot of detail on the PT part of it, but we can take a rock like this that has a very complicated garnet growth history and break it apart into different events, and we interpret that first growth of this zoned core, low pressure core, being at middle amphibolite facies, about 5 to 6 kilobars, so something like 15 kilometers deep. And then the high pressure event is similar to the Priest River, something around 10 to 11 kilobars. And then later, much later in its history, it undergoes a huge amount of decompression to where Andalusite is stable. This line right here shows the stability of Andalusite. So we have to bring these rocks from 35 kilometers depth to essentially less than 10 kilometers depth to grow Andalusite. What's interesting about this particular rock, though, is that it has this really complex metamorphic history, but the geochronology in terms of the monazite is all completely one age, and it's Eocene in age. And when we look in this sample at the monazite and where it resides in the thin section, what we tend to see are these clusters of grains that are aligned in the thin section, and all are the same age of around 46 to 48 million years old, and that's the only population that we see. And they have very consistent rare earth element patterns. And so our interpretation here, seeing very consistent patterns, these clusters that are aligned, and the fact that we've had this massive recrystallization of humongous kyanite grains, almost certainly has to call on some kind of fluids pulsing through the rocks to do that. And we've looked at, now this is somewhat old data. A couple weeks ago I collected data from 2 more samples, so we have 5 samples now from within the internal zone, and every single one looks the same. It's all 48 million. So there was a major fluid event that occurred during the Eocene as these rocks were brought up to about 10 kilometers depth that grew monazite, and essentially either probably reset any old monazite that had grown prior to that. It was just such a massive event that anything that was there before got recrystallized during this event. If we then go to a sample that's in the shear zone that bounds this zone of basement rock, we see it's a similar protolith. There are more reaction textures in the rock itself. There's abundant cordierite that rims some of these aluminosilicates. We still see kyanite converted to andalusite. We often see more sillimanite because the rocks have probably been heated a little bit more. You see rutile converting to ilmenite. That's a decompression texture. You see a resorption of some of those Cretaceous rims. On the data that we get from the shear zone yields a little bit older ages, from about 53 to 62 million years. So we get a range of ages. We see a little bit of the Eocene, the younger Eocene ages, but we don't see much. But we start picking up some older ages. And we only see these older ages in the inclusions inside of garnet. So when we look at inclusions in garnet, invariably, the inclusions inside of garnet are always Proterozoic. So we have looked at a lot of thin sections, and we never, ever see Cretaceous inclusions in garnet. They're always Proterozoic. And they're a range of usually between about 1.3 to 1.45 billion years old. And so that's been an interesting aspect, is every time we look at a sample with garnet inclusions, they're always Proterozoic. So these ages we would interpret to reflect growth during the shearing, during the activation of that shear zone and myelinization and exhumation of these rocks. So this gives us a sense of when that could have started at probably around 59 to 60 million years and continued down until 52 or so. And we see a lot of grains in these sorts of samples where we see mixtures, very complex mixtures of Proterozoic and Eocene ages. If we go outside of the shear zone and into the rocks that are in what we call the external zone, so outside of where this dome of basement rocks is, we're within strata of the belt at that point. When we look at those samples, we see a lot more complicated systematics. This sample is on the western side, and it's a garnet kyanite storolite schist, and it contains a lot of Cretaceous monazite and xenotime. And here the red is monazite, the green is xenotime. And what you can see here on the Concordia diagram is that it looks like there's actually two different mixtures, one between a Cretaceous component and a 1.3 to 1.4 component, and then a second mixture that is a Grenville age 1.1 component. and it's mostly recorded in the xenotime. And if we look at that in terms of the age distribution, we see ages ranging from about 55 to 84 million years in the younger population, and in the older population, it's mostly in this sample around 1.45. So again, right at the age of belt deposition. So we're essentially getting monomorphic ages that are of the same age as what we think when these sediments were deposited. And then we see the 1.3. And in this case, we have just one, I only kept the concordant ages here. So there's one concordant Grenville age, but we've seen that in some more samples. We're starting to pick up this Grenville age, which has been observed in some of the garnet lutetium hafnium age dating. So it's an interesting age from a tectonic point of view, because we're not sure what's actually happening in that area during that period in time. If we go all the way to the east outside of the core complex, still in belt rocks, this is from a Wallace formation schist. We're at storolite grade, garnet storolite grade. This is a large storolite porphyroblast. When we get outside of the core complex on the east side, we lose all Cretaceous and only see Proterozoic. So in this case, these are inclusions inside a storolite, and they both monazite and xenotime, and they range in age from about let's see, well, in here about 1.3 to 1.4. So if we look at all of the data that we've collected in the whole complex, we see these very two discrete metamorphic histories preserved in the rocks. The older history, seems to sort of culminate right around 1.4, but we see some ages that actually get greater than 1.5, which is really interesting from a point of view of, are these really belt sediments, or could these be actually be some sort of basement rock? It becomes difficult to tell when the rocks have been metamorphosed exactly what their sedimentary history was. But one of the most interesting things we see with these are that the inclusions are always, that's where the Mesoproterozoic tends to be preserved, inside of garnet, inside of old storolites, and that sort of thing. The dominant age is coincident with rifting, so we might have some rift-related contact metamorphism as those mafic sills intrude into the bottom of the belt. We might have some burial metamorphism from the weight of the belt sediment. Just the 1.3 may reflect just accumulating 20 kilometers of sediment and then metamorphosing the stuff at the bottom. But we see this very rich Proterozoic, Mesoproterozoic history that really wasn't identified in this area up till now. And then overprinted onto that is a similar Cretaceous history to what we see in the Priest River. And the big difference is that this pulse at 48 that's right in the core zone of the complex that we think is related to fluids. And the fluids are likely probably coming from, people have worked on the oxygen isotopes in the fluids, and it seems to be there's both meteoric water and magmatic water. And the magmatic water is coming from these syn extensional plutons, but there's also a big component of meteoric water, indicating these rocks were very shallow when that alteration occurred. So we can decipher this, this history that's really basically just on top of the Proterozoic history. And we can start to, when we look at these rocks in the field, it's really hard to tell sometimes what's what, because the superimposed metamorphic grades can sometimes be very similar in terms of the rocks that we see. So we can't just go in the field and say, oh yeah, this garnet is Mesoproterozoic, or this garnet is Cretaceous. So having this ability to do this in the thin section and tie it all together has been really critical. Okay. And just to give you a more graphic explanation of that, the samples that I showed you, this core zone that is all Eocene in age, I colored blue here. Then these yellow, which are the more complicated mixtures, have both Cretaceous and Proterozoic. And when we go outside the complex, in terms of the faults that bound these, then we get into entirely Proterozoic ages. So on the east side, we see 1.3 to 1.45. On the west side, we see 1.3 to 1.4, and we start to pick up the Grenville. And we see the Grenville in samples from the western side. We don't see any Grenville, any hint of Grenville on the east side. So it may be that this fault along the west side is really demarking where we start to pick up that 1.0 event. An interesting sample that we just collected this summer, and I just got the data on, it was from the hanging wall of this fault here on the western side of the this internal zone area, and we got all Cretaceous ages in a very narrow range of 75 to 78 with no Proterozoic. So that's kind of an interesting and different pattern. And it's in the Ravalli quartzite unit, in a politic unit within the Ravalli quartzite. So it's a different lithologic unit that contains all Cretaceous. So a very rich history from both the Proterozoic and the Cretaceous Eocene points of view. Okay. Yeah, just to summarize, what we link that to tectonically is this orogeny that occurred. We have evidence for it all the way up into the Yukon territory that's called the East Kootenai orogeny. The peak of that was at about 1.35. I think what we're seeing is the effects, though, of the original rifting. The older ages are related to the original rifting and rift-related magmatism, burial metamorphism, and the younger 1.3 ages are related to probably some crustal thickening that disturbed that basin after it formed and the sediments were deposited. But it's a regional medium pressure event. We see a little bit of the 1.1. The more samples we do, we start to pick up more of it, but it seems to be only on the western side outside the complex primarily. And the basic range of severe orogenesis ages is a bigger spread than what we see in the Priest River, but a similar sort of time scale. And then in terms of the core complex forming events, we see the timing of shearing followed by this big fluid event that we think is occurring very late after the rocks have been exhumed to near just a few kilometers beneath the surface. Okay, and then if you just compare those two complexes, then they both have some similarities in their Cretaceous history, some big differences in the Eocene histories. And essentially what we can say is the Clearwater complex, at least in the internal zone, has this extensive overprinting in the Eocene, whereas the Priest River kind of just came up passively. All of the deformations accommodated along the myelinate zone, and then the whole thing popped up without really being affected by the exhumation. Okay. So in the last few minutes, I just wanted to show you guys some data from the Ruby Range, and this is brand new data, and this is the work of my master's student, Drew Kramer, and he's giving a poster at GSA, so he's trying to pull this together. Doesn't quite have it all done, so I don't have this all as polished, but we've gotten some really interesting data, I think, from the Ruby Range, which is, of course, just south of Dillon. And what we're looking at there is the so-called Big Sky orogeny, or some people call it the Trans-Montana orogeny, this collision between the Medicine Hat Block and the Wyoming province that occurred around 1.8 billion. And these ranges in southwest Montana, the tobacco roots, ruby, blacktail, greenhorn, essentially have been thought of for decades as Archean crust, as we always just refer to it as the Archean in Montana, and that up until the last decade or so, really hasn't been recognized how extensive the reworking of these rocks could be, and the potential that it's not actually all Archean, that some of the material might be accreted Proterozoic crust in these ranges. So I've been working, had students working in the Highland Mountains, and most recently we've shifted to the Ruby Range, which is interesting because on the western side of it, of course, there are these world-class talc deposits that are hosted in the marbles, and we went here thinking, okay, if we have a chance to look at something that might be Proterozoic, we ought to look for something that contains carbonate rocks, because that could reflect passive margin type sediments that have been metamorphosed. So we did fieldwork this summer and just got some data a couple weeks ago. And we looked at 3 different areas. The first was around Stone Creek and some politic and orthoamphibolites that were in the marble, intercalated with the marbles in this so-called Cherry Creek suite of rocks. There's some spectacular migmatites that are down in the Elk Gulch area in the southern part. Dick's familiar with this because he's worked down there. There are these ultramathic plutons, part of the Wolf Creek plutonic suite, that are surrounded by these high-grade migmatites. They're very different from other rocks that we see. And then over in the Sweetwater area, on the eastern flank, around the Timber Hill area, we've been doing some mapping. My student Drew has mapped this area this summer, and we found some interesting stuff there. So just quickly, the Stone Creek area, which is on the western side, this is a garnet, cordierite, storolite, and thopholite schist, and it yields entirely Proterozoic ages of around 1.74 billion years. So these are all monazite ages. We didn't find any Archean or earlier Proterozoic ages in that. So metamorphism in those rocks is entirely Paleoproterozoic. A second sample from garnet silmonite gneiss, meters away from the orthoamphibolite, yields a similar spectrum, entirely Paleoproterozoic monazite, around 1.76 billion. So in the Stone Creek area, we see nothing but monazite that's part of this so-called big sky orogenic event. In the Elk Gulch area, this is the migmatite in Elk Gulch, and it surrounds these ultramafic pods and large ultramafic pluton. It's part of what we call the pre-Cherry Creek Suite, which is supposed to be the Archean. Well, it's all supposed to be the Archean, but these rocks should be older, interpreted to be older than the Cherry Creek Suite. It's another garnet silmonite-bearing rock, and it's hard to see because it's yellow, but we got one spot age that was about 2.35 billion, and from the same grain, another spot yielded a 2 billion age, and in that same grain, we saw the 1.8. So again, 1.75, so very tight peak around 1.75 in the monazite on that. And from an orthoamphibolite, actually, no. Oh, I didn't put that data in, but we also looked at an orthoamphibolite from that area, same exact ages. When we move over to the Sweetwater Creek area, which is all the way on the eastern flank of the Ruby Range, though, we see a different history. And in this case, these are all color-coded by grains, so each grain has its own color. In the previous one. In this one, we color-coded it by petrographic setting. So the black are matrix grains, the green are inclusions in sillimanite, red are in garnet, and brown in the rims of garnet. And these rocks, one of the characteristic politic lithologies is this very coarse-grained garnet sillimanite schist, or gneiss. This is a centimeter scale sillimanite crystal. And when we look at inclusions inside these sillimanites, these big sillimanites, we tend to see old ages residing in there. The green are inclusions in those sillimanite. We see some mixtures. Most of the matrix grains tend to be record the younger ages, but the two components here are 1.71 component and a 2.5 component. Still not quite into the Archean though. So we see this kind of earliest Proterozoic event preserved. And the interesting thing here is that we see color coded by age in the trace elements. We see a sweeping as we go from old to young and change in the growth environment of those. A second sample from Sweetwater. This is a rock that has about 40% cordierite in it, still garnet sillimanite bearing. And in the inclusions we looked at inside the cordierite, which is a decompression metamorphic phase that forms later in the history, we see that the cordierite, which is now green, on this diagram is recording the younger ages dominantly, whereas garnet inclusions, which are red, are recording more of the older ages. So this might, once we get into looking at the geochemistry more, and you can tie all these different dates together, but there seems to be a good correlation with the later cordierite, earlier garnet. And we see a similar kind of pattern of a change with garnet growth in the rare earth element patterns. So I think this really contradicts a lot of our thoughts about. And we know more and more that these ranges have been affected tremendously by this Proterozoic event, but I think this, utilizing this method is going to allow us to really tease apart get a chronology essentially of this collisional event that affected that margin of the Wyoming province. So. So to summarize that, we see only the Proterozoic, Paleoproterozoic over here. In the Cherry Creek, surprisingly, it's mapped as pre-Cherry Creek, older schist and gneiss, but the dominant metamorphic age is the same. The cores are 2.3, not 2.5. So there's this slightly younger reliced core, but very, very scarce, only 2 spots out of all that we looked at. And then the Sweetwater area over here has a very strong 2.5 component. And that age, what it's sort of been historically linked to is this Kenorland massive mafic magma emplacement event, rift event that metamorphosed the rocks, but not at a very high metamorphic grade. And we don't really have much petrographic evidence as to what that event actually corresponds to from a metamorphic perspective. But the important take-home point is that all of the rocks that we've looked at in the Ruby Range have a very strong Proterozoic overprinting. Okay, so with that, I'll just wrap things up, and hopefully I've shown you that this method that we're using really lets us get at these complex histories where we have multiple metamorphic events that have affected the rocks, and we can nail down processes like melt crystallization, fluid flow, with the geochemical fingerprinting of those events, and we can deconvolve the Clearwater areas as a poster child for this technique, because if you tried to use conventional techniques on it, you would just end up with a bunch of discordant data that you didn't know what to do with. And so we've really been able to actually deconvolve that into a logical sequence. Still, we don't know everything that's going on, but it makes more sense now. And these 2 minerals, I haven't talked at all about zircon. Zircon's an important one too, but I think for metamorphic histories, it's really the monazite and xenotime that are the most robust recorders of the growth and the modification of the continental lithosphere through time. So with that, I'll conclude, and I'm happy to answer questions.
Xenotime in a vein, would that indicate that the vein has been subject to some sort of later